Hi, everyone. My name is Maggie French. I am a postdoc here at Johns Hopkins, and I appreciate the opportunity to come and talk with you guys today. I do apologize for not being here in person, but I have put my email address on this slide right here in case you want to reach out after the session's over. All right, so I'm going to be talking about three different kind of categories of things today. I'm going to first be talking about learning health systems and how it relates to precision neurorehabilitation. I'm then going to talk about the infrastructure that we have at Johns Hopkins that's set up to create a learning health system that's focused on precision neurorehabilitation. And then I'm going to detail a project that we're doing that leverages this infrastructure to understand trajectories of recovery after stroke. So learning health systems were really brought to the forefront by the National Academy of Medicine Roundtable that first met in 2007. The vision of that roundtable is shown here, and they were really seeking to provide patients with the most appropriate care so that we're providing high value care. This essentially is saying that they want to be able to provide precision medicine to patients. Now, they identified that learning health systems were so important to this that they actually published their conclusions in a series titled The Learning Healthcare System. In this series, they define a learning health system with the definition that you see here. I want to highlight one part of this definition that really highlights that learning health systems identify that the information we collect as part of routine clinical care is an integral part of generating new knowledge about healthcare. And this idea has been formalized into a learning health system framework that you see here, where the system is working to address a health problem of interest using three iterative and cyclical processes and steps. The first is that they take clinical practice and use it to generate data. They then take that data and use it to generate new knowledge. And then they take that knowledge and use it to change clinical practice. And through this process, the system addresses whatever problem they're specifically interested in to improve the care that patients provide. Now, this system, a learning healthcare system, is really an important part of precision medicine. And this has been highlighted in several publications, including the one that you see here, where the authors specifically say that learning health systems can support and catalyze the delivery of precision medicine. They say this for a couple of reasons. So precision medicine is really aiming to provide the right care to the right patient at the right time. In order to do that, we have to be able to identify biomarkers that help us understand what's going on with each specific individual. And learning health systems allow us to do that. They do that in a couple of ways, one of which includes that learning health systems allow us to generate large databases that have information about heterogeneous groups of patients that reflect the care that we actually provide on a day-to-day basis. Additionally, learning health systems have that step that was in red in that cycle that I showed before, where it wants to take the knowledge we gain and put it back into clinical practice. And so completing precision medicine within a learning health system allows you to acknowledge and appreciate the barriers to clinical care that's important to consider when we want to move towards precision medicine and precision rehabilitation. Now, precision neurorehabilitation really requires that we do a couple of things. In particular, I've listed 6 things here that we need to do to move towards precision neurorehabilitation, including to generate and curate large heterogeneous databases, collect standardized and precise measures of function, synergistically use different study designs, develop predictive models, and then leverage system and team science. And so broadly, these 6 different things that are required for us to move towards precision neurorehabilitation can be kind of summarized with these 3 different categories. So what I want to do is map these categories of things onto that learning health system framework to really draw that link between precision neurorehabilitation and learning health systems. So in a learning health system that's focused on precision neurorehabilitation, the health problem of interest is variability in patient outcomes. The data gathering that I talked about on the previous slide maps onto the practice to data step. The data analysis maps onto the data to knowledge step. And then implementation is integral to the knowledge to practice step. And then collaboration really spans the entire framework. So I want to talk now about what we're doing at Hopkins to create a learning health system that's focused on precision neurorehabilitation. A group of folks earlier talked about what we've done to standardize what assessments we collect on patients across acute care, inpatient rehab, and outpatient here at Johns Hopkins. So I'm not going to rehash that, but that standardization is a critical part of this practice to data step within our learning health system. In addition to standardize what's being collected, we have to standardize how it's documented as well. To demonstrate this, what I've done is I've pulled data from one field in our medical record that documents gait speed. What should jump out to people is that this y-axis is pretty big. The highest value is 40 meters per second, but healthy gait speed is about 1.2 meters per second. So something funky is going on with this data. What's really happening here is that we have some clinicians who are entering actual gait speed. Then we have other clinicians who are entering how long it takes them to walk the patient to walk a distance. And so because the medical record doesn't specifically tell clinicians what data is expected in that field, we end up with this type of quality of data, which we really don't want to be using to generate new knowledge. So in partnership with Kelly Daly, who's a healthcare informatician here, she created a new field within the medical record that more clearly states what type of data is expected in that field. So here's data from that newer field. The y-axis, again, I want to highlight. The highest value here is now 6, so definitely a much improved from the older field shown on the left side here. And what should really jump out is that a vast majority of these observations are well below 2 meters per second, indicating that the simple change in the documentation system really helps facilitate this process of generating data from practice. Now, also within this step of practice to data, we wanted to be able to access this data. And so we created the Rehabilitation Data Repository in partnership with the CCDA as well as the IRB. The folks you see here, Sharon, Michael Cook, and Bing Ching have been an integral part of making sure that we have the data that we want within this repository so that we can answer the questions we want to answer. This repository includes all sorts of different information from the medical record. So for example, it includes information about when they make an encounter with our healthcare system, whether that's an ED visit, an outpatient visit, or an inpatient admission. We also have information about their function from rehab visits. So that standard battery that you've heard about, all of that information is within our data repository, as well as other information that rehab professionals document. And then you can see we have a whole list of kind of other categories that we're getting data from the medical record. Now we're also pulling in data from publicly available data sources to enhance this data. Examples of this include data from the census as well as state health exchanges so that we can make this database even more robust. As of right now, we have over 18,000 individuals with stroke who we have data for within this data repository. And so that allows us to then use this database to take clinical practice, have it turned into data, and then use that data to generate new knowledge by having subsets of this data from the data repository being pulled out as separate IRB protocols so that we can answer specific questions with only the data that we need. The third step of that learning health cycle is taking that knowledge and turning it back into practice. So we are not really ready to implement anything just yet, but we're getting our system ready to do so. So in partnership with John Scott, who you see here, he's a software engineer, we're working on developing dashboards that allow clinicians to visualize people's functional status. So here in this screenshot, what I'm showing is gait speed on the y-axis, and then the x-axis is time. And you have each kind of time point when this measure is made for this particular individual. And what this allows us to do is have first, clinicians have a way now to see this data in a really nice longitudinal fashion. But the other thing that this does is it gives us the foundation or the platform that as we build models from our medical record data, we have a place to implement those models so that we can come back to our clinical team. Again, we're not at that stage yet, but we're laying the foundation to do that. So within our learning health system, we have a number of different questions that we're working on answering related to precision rehabilitation. And so I want to take a moment to talk about one project in particular that we're doing in this data to knowledge step. And this project is really working on trying to understand trajectories of functional recovery after stroke. So to get started, I just want to talk about what a recovery trajectory is. To do that, I want to illustrate it with a figure. So on this figure, on the x-axis, we have time since stroke, and on the y-axis, we have some arbitrary measure of function. So we have 3 individuals here with their measure of function at time of stroke, and then again at 3 months after stroke. And these people look like they recover pretty much the same. You know, a little bit of difference, but for the most part, they're very similar. But if you have measurements between these 2 different time points, for example, at month 1 and month 2, you start to see that maybe these people actually recovered a little bit differently. And if we kind of fit a line to these individuals, you see that even more pronounced, where this person in light blue recovers pretty quickly until a month after stroke and then kind of plateaus. But this person in gray has kind of a slower rate of recovery, but continues improving throughout that 3-month period. And so these recovery trajectories are characterized not just by the extent of recovery, but also the rate of recovery. And so what we want to try to do here is identify what factors are related to recovery trajectories, particularly for functional mobility after stroke. And then we want to ultimately be able to predict the recovery trajectory related to mobility after stroke. So I'm going to show you the very beginning of our work towards this. I'll go through kind of the methods and results, of course, but I don't have kind of a final predictive model to show you guys. And this is a kind of a large task, and so we're still in the works of that. But I do want to show you what we have done so far. So this is a retrospective cohort study. We're using data from that rehab data repository that we just talked about. The cohort's defined as individuals who are over the age of 18 and were admitted to the Johns Hopkins healthcare system with measurements of functional mobility at required time points. Our measure of functional mobility is the AMPAC, or the Activity Measure for Post-Acute Care Mobility Score. We are using T-scores here. And the AMPAC, for those of you who aren't familiar, is a self-reported measure of somebody's functional ability, specifically related to mobility. And so it includes questions about how much difficulty people have doing different mobility tasks, such as walking to the bathroom, walking a mile, etc. And to build our cohort, what we've required is that an individual have a measurement of AMPAC mobility at least 4 different time points. They're required to have one at admission and at discharge from the hospital, and then they need to have at least 1 measurement at either 60 or 90 days. So everybody will have at least 4 measures. Some folks will have 5. The predictors that we're currently examining fall into 2 categories. The first is demographic information, which we're going to use specifically age, sex, and depression. And the next is admission information, so specifically length of stay, the type of stroke, and then the PT dosage, which I'm defining as the average minutes of PT per day following evaluation by physical therapy. In other words, if somebody was admitted on Monday, for example, and then they weren't evaluated by PT until Wednesday, I'm not including the days prior to the evaluation within this average. From a statistical standpoint, we're going to use linear mixed effects modeling. Linear mixed effects modeling may be new to folks, so I want to walk through it for a second and talk about why this is advantageous. So linear mixed effects models allow us to account for correlation of observations. And of course, in longitudinal data, including recovery trajectories, we have correlated data where this person in pink has an observation at time 1, time 2, and time 3, which are going to be related because they're coming from the same person. And so linear mixed effects modeling allows us to have those correlated observations. It also allows us to have missing data. So in this example of folks, let's say that this person in yellow didn't have a measurement at month 2. That would be okay. We wouldn't have to throw this person out entirely. We would be able to use their other measurements of mobility and just not have one for month 2 for them. Additionally, linear mixed effects modelings allow us to estimate individual intercepts and slopes for each person. So what I've done here in the figure as an example is I've plotted the group average on top of the individual data, And what linear mixed effects modeling allows us to do is have a individual or a random intercept for each person, meaning that the group averages this point where my laser pointer is, but this person in green is allowed to vary from that point a certain amount, and that's called a random intercept. Additionally, it allows the slope of the line to differ between people. So again, you have the group average in black, but then this person in green looks like their rates very different. And so for that person, you'd have a slope that varies from the group mean, which is called a random slope. Now, depending on the complexity of your model, you also don't have to have a linear line, but you can have individual estimates for all of those parameters through linear mixed effect modeling, and that's exactly what we'll do as we move forward with the talk today. So here's some information about the cohort. We're including 553 individuals, all of whom have at least 4 measurements of the AMPAC mobility within the first 3 months after stroke. You can see other demographic characteristics shown here. These are all metrics that we'll be using in our modeling as we move forward. I also want to show you the raw AMPAC scores. So here are the AMPAC T-scores for all of our individuals in the cohort at time 0, which is at time of admission, time 1, which is discharge from the hospital, time 2, which is 1 month after stroke, time 3, which is 2 months after stroke, and time 4, which is 3 months after stroke. And what you can see here is you can kind of see that there's a trend towards improving as you get to 3 months post-stroke. Now, this these are box plots, so you can kind of see the variability. But to highlight the variability in our cohort of 553, I want to show a spaghetti plot. So this is a spaghetti plot where the gray lines indicate each individual in our cohort, and then those black diamonds represent the average AMPAC mobility T-score in the sample. And what you can see here is that there's an awful lot of variability in where people start, as well as in how people change. Some of these people look to be flat, some of these look to be flat, some of these seem to be going up. And so there's a lot of variability that linear mixed effect modeling may be really useful for modeling and understanding. So when we start doing linear mixed effect modeling, the first thing we have to do is determine what the most appropriate type of model is. And so to do this, we're going to compare 4 different types of model. In all of these 4 different types, I'm going to walk through and tell what is being tested. And over here on this side of the screen, it's kind of a visualization of what that model looks like. So the first model that we'll test is just a traditional regression where we have just an intercept and we're assuming it to be a straight line. And so in that setup, it would explain the data, this whole sea of mess with just a horizontal line shown in red here. The next model we'll test is a random intercept model. And so in this model, people can start at a different place, but we don't have any sort of slope. And so they're all just have a single straight line to represent one person. We can then add a random slope. So now, again, we have different starting places, so a random intercept, but people's slope over time is also allowed to be different. And then finally, what we'll do is we'll look at a model where people are allowed to have a random intercept, so start at a different place, have a different slope, but also have different amounts of linearity. So shown in this plot here, you see this person in red has a kind of more of a curve to their line compared to the person in green. And this person in orange has a more rapid increase and then they kind of flatten out. And so the quadratic term is what we add here to assess that nonlinearity. And what we do with linear mixed effects modeling is we want to know which of these 4 different models is best, and then we'll add the factors that we're interested in into that model. And so to do this, we do a series of model comparisons, and we specifically are comparing on these 3 different fit statistics, the AIC, the BIC, and then a chi-square test. Here are the results of those 4 different models. And all you really need to know is that a lower AIC is better, a lower BIC is better, and then a chi-square test that is significant means that the model on the bottom is better than the one above it. And what the kind of summary and take home from this plot is, or excuse me, from this table is, is that this linear mixed effect model that has a random intercept, a random slope, and a random quadratic slope, i.e. rate, is the best model compared to the other three. And so this we're going to use as our baseline model as we go in and try to assess the impact of those different factors we talked about before. So again, to assess the impact of those different factors, we're going to do a model building exercise where we start off with that model that we just talked about, and then we add in the factors that we're interested in a series of increasingly complex models. So model 1 here has the random intercept, slope, and rate, and then we add in the demographic information. We then increase the complexity by adding in the admission information. And then we increase the complexity even more by adding interaction terms between the demographic and admission information and time. And then we can increase it one more time by adding in interactions with the demographic and admission information and that rate, which is the quadratic of time. And what you can see here is that each of these models tests a different thing. Some of them test just the impact of these factors on the intercept. Some of them tested the impact of these factors on the intercept as well as the slope. And then this model 4 here tests the impact of these factors on the intercept, the slope, as well as the rate. Again, you can see these same model fit statistics. I'm not going to go into detail and walk through all of these fit statistics, but if you were to look at these long enough, you would identify that model 3 is the best model here. And so this is the model that we're going to dive into. So first, what does this model look like? All right, it has a random intercept and a random slope. What does that mean? Well, if we pull out the data for 4 people from that sample of 553, this is what their data looks like. The dots here represents the actual data for each individual. It's color-coded. And then the lines are what the model predicts for that particular individual. So in green here, you see that they start at this point, and then the model predicts that they have kind of a curvature where they continue to improve over time. This person in purple has a different starting point. They also have a different slope, and they have a different curvature. And so this is very similar to what I showed you before when we were talking about how to identify the most appropriate model. We're allowing everyone to have a different starting point, a different slope, and a different curve to their line. So this is only 4 people of that 553. Here's the same information, but for everybody. And again, you can see all of those things everyone's allowed to have their individual intercept, slope, as well as curvature. Now from this model, you get beta coefficients for all of the predictors that you put in. And so I'm not going to go through this table in a ton of detail, but you can see that we have some factors that are significant predictors of these trajectories. And what I want to really highlight is I want to dive into these 3 that I've now highlighted in red. And we'll start with the PT dose specifically. So I've created 3 subgroups from our data where some people get a limited amount of therapy minutes per day, an average number of therapy minutes per day, and a high number of therapy minutes per day. And what you can see here, particularly if you compare the limited and high group, is that these groups do in fact look different in terms of intercepts, as well as in terms of the slopes. And that's exactly what those coefficients and what the significant and not significant is telling us. We look at the same thing, but with age. Now I've divided our data into 4 groups: the youngest or younger group, younger average, and older group. And again, you can see that these groups have a different starting point. They also seem to have a different rate, a different slope, and they seem to have a different curvature. And this is particularly evident when you look at the older group and compare it to the younger average or the younger group. Now, what's also evident in this plot is even though there's differences based on age, there's also a lot of variability within each of these kind of subgroups that I've made. And a statistic that we can use to understand that better is the marginal and conditional R-squared. So the marginal R-squared is telling us how much of the variability in our data is being explained by all of these factors that you see in these two tables, the fixed effects. And that's really small in our data, actually. These fixed effects are only explaining 17% of the variability in our data. This conditional R squared, on the other hand, is really high, 0.78. What this tells us is that the fixed effects, so all of these, and those individualized intercepts, slopes, and rates are explaining almost 80% of the variability in our data. And what this really highlights is that even though these metrics are significant, it seems like they actually probably have really poor predictive power, really highlighting that association doesn't mean prediction, and that we have more work to be done to really understand the variability of this data. To highlight kind of what this conditional R squared is also accounting for, I've plotted here the distributions of the intercept for our entire sample, the slope for the entire sample, and the rate for the entire sample. And what you can really see here is that, the fixed effects are explaining a small portion of the variability, but then us allowing people to vary on where they start as well as how they change, there really is a lot of variability that's not accounted for by those fixed effects. And so future work that we do to try to understand these recovery trajectories can really hone in on these individualized predictions of the intercepts and slope and rate to try to understand people's recovery and to try to predict that recovery for future patients. So in conclusion, learning health systems are a really useful way for us to move towards precision neurorehabilitation. And when we think about examining recovery trajectories, there is a ton of variability, and we really need to be thoughtful about what types of statistical techniques we use, as well as what factors we explore for their predictive ability, and focusing on predictability rather than just associations. I'd like to acknowledge my funding sources, including the NIH and the Sheikh Khalifa Stroke Institute. I've acknowledged several people throughout the presentation, but I also want to acknowledge the individuals that you see here for their leadership on this work. And again, I apologize for not being there in person today, but here is my email once again, and I'm happy to answer any questions via email should you have them.